everybody, it's Mrs. Pound with our third and final video for Chapter 25 on vibrations and waves, and we're going to take a look at a couple of special topics today. So our objectives are going to be to describe the Doppler effect for sound and relate it to the blue and red shifts for light, describe the conditions for a bow wave to occur, and describe the conditions for a sonic boom to be heard. So let's first look at the Doppler effect, and all of these three things are related. The Doppler effect is a change in wave frequency due to the motion of the source or the receiver. There can be a blue shift, which there is an increase in frequency, or a red shift where there is a decrease in frequency. And actually, this red shift and blue shift applies to astronomy. There is actually a red shift in the light that we see from stars. And so we know that the universe is expanding, moving outward because of this red shift. And the greater the speed, the greater the Doppler effect. So let's take a look using the example of a jiggling bug at why this occurs, this red shift and this blue shift. So here I have a bug jiggling. Go ahead and pause the video and draw this picture. And you can even put some legs on your bug. I just put a dot. So here is a bug, and it is bobbing up and down. I tried to represent this with my arrows here, which it looks like it's going side to side, but it is going up and down. It's kind of hard to sometimes do a three-dimensional concept in 2 dimensions. So this is up and down, not side to side. So this bug is bobbing up and down, and it is moving to the right. Now, if it was bobbing up and down, it would create a pattern and it wasn't moving. It would create a pattern a lot like a raindrop, okay? But it is actually moving to the right. And so what you see is the waves bunch up here, and they occur at a higher frequency ahead of the bug, then behind it, there is a lower frequency. Now, the speed of the waves is still the same. It's just the frequency that has changed. And so it appears as if it is the case that the frequency is higher here and lower here. So if it is moving away from an observer, they see lower frequency. They see a red shift because red light waves have a lower frequency than blue light waves. And if you are an observer over here, you see higher frequency, which is a blue shift if it is moving towards you. And so this is how astronomers know that the universe is expanding. Now, this also applies to sound waves. I'm sure you have had the experience where you're standing still, and as a car comes toward you, the sound increases in frequency. There's like this meow sound. It increases in frequency as it comes toward you, decreases as it goes away from you. Well, this is due to the Doppler effect. So, as the sound of a car's horn comes toward you, the pitch of the horn increases, or the pitch of the car itself, the engine. As the sound of the car's horn passes and recedes from it, the pitch of the horn decreases. So that's the reason for that sound. The speed of the sound wave from the source remains the same. So the speed is the same, it's the frequency that is changing. Now let's take a look at bow waves. Bow waves are formed by overlapping crests of waves produced in a medium when the speed of a source is greater than or equal to the speed of waves it produces. And we see that with a speedboat back here. These are bow waves coming off the back of the boat. They are V-shaped, as we can see. They are two-dimensional, and they are created by speedboats. So let's take a look at what happens. So we're going to go back to our bug. This is our bug when its velocity is less than the velocity of the waves. This is the bug when its velocity equals the velocity of the wave. See how they've all bunched up. Now it's going faster than the velocity of the waves, and so we're forming this V shape behind. These are our bow waves, and we can see that there is constructive interference going on here. And so those waves, the amplitude gets really high. And so if you are in another boat or you're on the shore over here, you are going to get splashed by these waves. They're going to hit you right here if you're standing here. Now, if somebody's standing over here, they haven't hit them yet. If they stood here, they're already wet. Let's take a look at shock waves. A shock wave is formed by overlapping spheres that form a cone. It's created by supersonic aircraft and it's three-dimensional. So it's going to be a lot like the bow waves, except for this time, instead of being two-dimensional, it is three-dimensional and it has to do with air pressure. There are two parts. Number one, there is a high pressure caused by superposition of compressions and low pressure caused by superposition of rarefactions. So you cannot see these waves, but you will feel and hear them when this hits you. And when you feel and hear them, you will experience a sonic boom. This is sound created by a shock wave. It's created continuously as long as the source travels faster than the speed of sound. And so I want to go back to this picture. You don't have to draw this again. You should already have this drawn at your notes in the other spot. I gave you room. But what happens is now we have compressions and rarefactions. And a person here, now I think we have this conception, if you've ever heard of a sonic boom, you probably think that it just happens once when a supersonic aircraft hits what we call the sound barrier and it produces a boom when it does that. It does not. It is actually continuous like the bow wave. But what happens is somebody who is positioned here is not hit by it yet. If you're positioned here, you're experiencing it. If you've positioned here, you're already happened to you. It's like being splashed by a bow wave, except for now you're being hit by a shock wave. So it is in fact continuous, and you will hear and you will feel it. Now, some examples also are a whip, a bullet, and a towel. So that crack you hear from a whip, that is actually a sonic boom. The sound you hear from a bullet, sonic boom again as it goes by, and a towel, you can snap a towel and create your own sonic boom. You don't have to be in a supersonic aircraft. So our objectives today were to describe the Doppler effect for sound and relate it to the blue and red shifts for light, describe the conditions for a bow wave to occur, and describe the conditions for a sonic boom to be heard. So this is our last video. Don't forget your 5 questions and start studying for your test. You have all the material you need.